Hello and welcome everyone. In this video we will be solving the disks intersections example of the Codility lesson number 6. We're going to explain the algorithm and then we are going to write our code in C++ and in Python. Now before we start, it's good to know that this is one of the most challenging examples in the Codility lessons. So you might want to pause the video at some point and rethink some ideas and maybe repeat some parts more than once in order to understand all the details leading to the most efficient solution. So just if you are struggling for the first time with this example, this is completely normal. Give it enough time and things will get easier as you are working around the problem. So first we are given an array containing the radius of different disks, and the index of the array represents the positions of the centers of these disks. So you can imagine an axis where these are the indexes, and for each index we are provided the radius of the disk around this precise point. And the target is to write a function that returns the number of intersecting disks, and if the number of these intersections is greater than 10 million, then the function should return -1. We can start thinking with a brute approach, meaning for each disk in the array we're going to test all the other disks and see if they intersect with this particular disk. But this would mean that for each element of the array, we're going to test all the other elements, and this would lead us to a complexity of n squared, n being the size of the array. Just as we have explained in other videos on these Codility examples, the brute approach is probably the slowest solution you could think of. We always start with this, putting our algorithm using this method, but then we try to improve in order to reach a more efficient solution. One important point here is that in all our solution, we're going to consider the points where the disks intersect with the axis. So when we say starting position or center position, we're always referring to positions on the axis represented in the example. So if we take this axis and we consider all these disks centered at all these points, 0, 1, 2, 3, and so on. The first disk is centered at position 0. It has a radius of 1, so it covers the area between -1 and +1. Then we have the disk at position number 1. It has a radius of 5, and it covers the area between -4 to +6. So these two disks, they intersect because the value of the position C plus R of the first disk is higher or greater than the position C minus the radius, the center position minus the radius value of the second disk. So this is the expression we can use in the brute approach, and we can increment a counter every time we detect this condition is true. A more efficient solution would be reading the array a minimal number of times. So we're going to start by defining a new vector containing the lower positions of the radiuses of the disks, or where these disks are intersecting with the axis. For example, these are the positions on the axis, and we have the first disk. It has a radius of 1, so it's starting at position -1, and I'm going to save this position in my new vector. Then, for example, the third disk has a radius of 2 and it's starting at position 0. So also we're going to save this position in our new vector and so on. So we will obtain a vector, let's call it S, meaning the starting positions on the axis of the disks, where the element Si is equal to I minus Ai. However, we are going to keep only the positive values. All the negative values will be replaced by 0 because all the disks starting at a negative position are considered to start at position 0. Then we are going to define a new vector containing the upper positions of radiuses intersection with the axis. So this is our axis. We have the positions. The first disk at position 0 has a radius 1, and so the highest point that is reached by this disk is positioned at +1. So I'm going to keep this position in my new vector. Same thing for the other disks, and so on. So my new vector, let's call it E, meaning the end of each disk, contains only positive values, where the elements EI are equal to I plus AI. However, just as we've done previously in the previous vector, we have to replace all the positions that are exceeding the boundaries of our array, which is the same size as the array A, by the highest position available in this array E. So we're going to check these into details later on. Just keep in mind that it's mainly a way to avoid exceeding the frame of our problem. which is all confined within the size of our vector A. So now going back to our example, these are the values we're going to have in our vectors S and E. So 0 minus 1 is equal to minus 1. So as you can see, it's a negative value, so it was replaced by 0. Same thing here for the second element. 1 minus 5 is minus 4, so it's negative position. We are going to replace it by 0 and so on. Just for the positive values, 3 minus 1 is equal to 2, so we're just putting the value as it is. And the last element, 5 minus 0, is equal to 5, so we just replaced it by 5. 0 plus 1 is equal to plus 1, so it's good. We're going to put it here at the end or the E vector. 1 plus 5 is equal to 6. It does exceed the boundary or the maximum size of our array, so we are going to put the maximum available position, which is the position number 5 instead. So these are the positions we have replaced that were holding negative values. And these are the positions that were exceeding the maximum position of our array. They were replaced by the highest available position, which is position number 5. Then we're going to define two additional vectors containing the counts of each number in vectors S and E. So for example, the first element here, number 4, for the position number 0, it means that we had 4 positions 0 in the vector S. So position number 1 has a count of 0 because we have no positions number 1 here in the vector S. We have one position number 2, which is true. It's the only one here, and so on. Same thing for the vector CE. It's the counter of the ending position values. So position 0, we have none. No disks are ending or closing at position number 0. We have one disk closing at position number 1, which is true. We have one number 1 here. We have 0 for the number 2, 0 for number 3, and 2 are ending at number 4, which is true. We have 4 here, and we have 3 at or beyond the number 5, the position number 5. Remember that we have replaced some of these values by 5 because they were exceeding the maximal position, which is the position 5. So anyway, we have these two vectors so far. Then we are going to define two additional vectors, which are the cumulative values of vectors CS and CE. So we are going to call these CCS and CCE. And notice the values, for example, in this vector, we are starting at 4 because here so far we have the count number 4. Then we're adding 0 at this point, so it will remain 4. Then we're adding 1 at this point. The 4 becomes 5. 4 plus 1 is equal to 5. 5, 5, and at the end, we reach a maximum value of 5 plus 1, which is equal to 6. So this is the cumulative or the sum at each position of this vector, of the elements of this vector. Same thing for the vector CCE, which is the cumulative value of the counter of the ending positions. So this is a key point here to understand how we've reached these two vectors. If you haven't followed everything so far, I would advise you pausing the video, going back, probably watching again, just to understand the exact content of these two vectors. Basically, this is the sum of the number of disks that were already, let's say, opened or started before or at each position. And then the other vector here represents the sum of the number of disks that were closed or reached their maximum higher point at or before each position in the vector. So these two vectors will allow me to access the number of disks that are covering a certain position simply by doing the difference between the number of disks that were started so far at or before a certain position and the number of disks that ended just before this particular position. So by doing this operation, CCSI minus CCE I minus 1, we can obtain the number of disks that are covering position I. Remember that the problem considers that these disks also contain their edges, and this is to be kept in mind while doing this particular operation. If it wouldn't be the case, we would simply do CCSI minus CCE I instead of I minus 1 here. Now, if you are curious enough, we can verify these values on the figure of the provided example. Let's check position number 0. We have 4 covering disks. Remember, we are taking into account the edges. So if we count these, we have this big disk, 1, 2, and 2 edges 3 and 4. So we have 4 disks covering position number 0. Same thing for the position number 1, then the position number 2, 3, 4, and at position number 5, we have 3 disks. We have this big disk, 1 and 2, and we have this small disk with the radius equals 0, which is centered at position number 5 too. So we have 3 disks actually covering the position number 5. Okay, now we've reached a critical point in our algorithm. We have to count the number of intersecting disks. We have all the elements we have already calculated, and we're going to start by calculating the difference we've talked about between CCSI minus CCEI minus 1, which will provide us the number of disks covering a certain position. And we're going to remove from this value the number of disks that are centered at this particular position. Because the idea is that at each position, we're going to take the disks that are centered there and check with how many other disks they are intersecting. So this value here between parentheses is equivalent to the number of disks covering the position I, except those that are centered at position I. So we're going to multiply this value by the number of disks centered at this position I, and we're going to include these values into a sum while reading the array elements. Now, since we could have more than one disk centered at each position, and we have already removed those from our previous expression, and considering that these disks can be intersecting with each others, which wasn't taken into account in this previous expression, we have to add the number of their mutual intersections. So this is going to be CSI times CSI minus 1 over 2. If you are not familiar with this expression, it's something coming from combination mathematics. You might find it online or Google it. It's going to provide us the number of mutual intersections between the elements CSI centered at position I. So finally, we have our magic expression. The first term takes into account the intersections of disks centered at position I with all the other disks, and the second term represents the intersections of disks at position I with each other. And this solution is supposed to be more efficient than the brute solution, because once you have this expression, you run through the array only one time, so it's a single for loop that would provide you the final result. However, you have seen that it requires some kind of preparation, as we have added new vectors that are needed for this particular expression. So this is our solution in C++. This is our function. It takes one parameter, the vector a, and we're going to start by testing if a is empty. In this case, we are returning 0. If not, we continue our problem. We are defining our new vectors. Remember, we have to define vector s, which are the starting position of each disk. And then we have the vector e, cs, and ce so far. All of these vectors are holding zeros as initial values, and they are of the same size of vector a. Then for I going from 0 to the size of vector a, we're going to test if any of the elements I minus ai is negative or equal to 0. These are the starting positions that are negative before the position number 0, in which case we are going to replace these elements in the vector s by the value 0, which is the lowest position available in our vectors. Otherwise, if we have a positive value, then we are simply going to take it as it is, and we're going to store it in our vector s. So it will be si equal I minus ai. Same thing for the vector e. If any of the values I plus ai are going to exceed the maximum position of vector a, we are going to replace these values by the maximal position, which is a.size minus 1. Otherwise, we are going to take the value I plus ai as it is and store it in our element ei. When this is done, we're going to increment the counters in vectors cs and ce. The counter cs of the element si is going to be incremented by 1, and same thing, the counter ce of the element ei is going to be incremented by 1. So when these vectors are filled, s E, CS, and CE. By the end of this for loop, we can define two more vectors, the CCS and the CCE, all of the same A.size and holding elements number 0 as initial values. And the first elements, CCS0 and CCSE, are going to be equal to the first elements of CS0 and CE0. And this is basically to avoid putting I equals 0 here at the start of our iteration. And since we are using I minus 1, we would fall out of the boundaries of our vectors. So the first elements are done manually here, and then we are going to use a for loop starting I equal 1 to A.size, and we're going to increment our counter I, and then we are going to do the following. CCSI will be equal to CSI plus CCSI minus 1, which will be our way of calculating the cumulative values of vectors CS and CE and storing these cumulative values in vectors CCS and CCE. And finally, we reach our final operation, which is calculating the sum of intersections. So we're going to define an integer variable s equal to 0 at first, and we're going to iterate over I equal to 0 up to A.size excluded. And we're going to increment our sum. S plus is equal to the expression that we have already explained in the algorithm. And when this is done, we have our number of intersections. If this number is exceeding the value of 10 million, we should return -1 as required by the problem itself, the problem description. Otherwise, we're going to return the value of S, which will be holding the sum of intersections. So this is our solution in C++. Now let's go and see how it is done in Python. We have our solution function that takes A, the list, as an input parameter. Then we're going to test if the length of A is equal to 0, in which case we are returning 0 as a result. And we're going to define our four vectors, SE, CS, and CE, initialized at 0 with 0 elements, and of the same length of list A. Then we can start by filling these vectors with their values using a for loop. So for I in range 0 to length of A, we're going to test if the elements I minus AI are negative or equal to 0, in which case we are going to replace these values by 0 in the vector S. Or otherwise, we are going to take the values as they are. Si is equal to I minus AI because these are positive values. And same thing for the vector E. If the value I plus AI is higher than the maximal position in the list A, we're going to replace these values by the maximal position itself, length of A minus 1, and we're going to store this value in the vector E. Otherwise, EI will be equal to I plus AI. Once we have filled the values of S and E for the position I, we can include them in the counters vectors, CS and CE. So we are going to use these two expressions to increment by 1 the values of CS with index SI and the value of CE with index element EI. Then we can proceed and calculate the cumulative vectors, CCS and CCE. We initialize these using 0 values with the same length of vector A, both. And then we are going to initialize the first element, CCS0 is equal to CS0, and CCE0 is equal to CE0 for the first, because then we are going to run our for loop starting from the second element with index 1 up to length of A. So in this case, CCSI will be equal to CSI plus the previous element, which will give us the cumulative values of the vector CS, and we're going to store these values in the vector CCS. Same thing for the vector CCE, which will be holding the cumulative values of the vector CE. Then we reach the final part of our program, where we have to calculate the sum or the total number of intersections among these disks. So I'm going to initialize a first variable at 0, and we're going to run a for loop from position 0 to length of A. And if I is equal to 0 at first, I'm simply going to use this expression where CCSI minus CSI times the centered disks at this position I, CSI, plus mutual intersections between all the disks that are centered at position I. Notice that I have removed this element here, CCSE I minus 1, simply because when I is equal to 0, we don't have an element CCE I minus 1. In C++, we didn't do this because by default we would get the 0 value in this case. So it's kind of cheating. We shouldn't have done it, but we got away with it. It made our code slightly shorter. We didn't have to put this if condition here to avoid the problem. However, in Python, it is detectable and it's going to give us an error or at least a wrong result. So we had to include this if condition. So in case I is equal to 0, we're not going to include this particular element here. Otherwise, we can use this expression that we have explained in our algorithm. Then when the for loop is done, we have to test if our total sum is higher than 10 million, in which case we are returning -1. Otherwise, we simply return the value of total. Notice the integer cast here in Python, which we didn't have to do in C++ because we've already defined our variable here, the sum variable, as integer. But in Python, we simply declared our variable and Python took care of the type of the variable automatically. And at this point, Python saw that it is better that this would be a floating value. Since the problem requires an integer return value, this is what is required on the Codility website, this would cause us a problem. So we have to cast our result into an integer value. So that's it. This is all I have to tell you. I hope you guys found the information helpful. Thank you for staying that long. Remember to stay patient when practicing your algorithmic skills, and good luck to you. Hope to see you next time.